So in this problem, we're given that a block of mass m is going to be accelerated up a ramp with a counterweight of mass 5m pulling it downwards with a acceleration length L and a ramp angle of theta, and what we're asked is how high off the ground this mass little m is going to get after it gets launched. After it reaches this point, it's released from the rope and allowed to just fly in free fall up through the air. And the ramp has total height h naught. So the way we're going to actually solve this is we're first going to find the launch velocity of the little mass when it reaches the top, and we're then going to solve using integrals over the acceleration to figure out how high it gets off the ground. So first we're going to draw some isolation diagrams. The big mass 5m has the tension force from the rope pulling it upwards, and the force of gravity pulling it downwards, and we're going to define the downwards direction to be positive. The little mass has the force of tension pulling it upwards along the slope, normal force pushing it away from the surface of the triangle, and the force of gravity pulling it downwards. And in this case, we're going to define upwards along the length of the rope to be positive. So now this allows us to use our F equals ma equations. So for the little mass, we get F equals ma equals t minus mg sine theta, and that's because this normal force cancels out the mg cosine theta term for the y hat components. And for the other block, we get the sum of forces equals 5ma, because it's got a mass of 5m, equals just 5mg minus t. Now because these two blocks are connected by a rope, they have to accelerate at the same rate. So what that means is that we can add these two equations together, and we ultimately get 6ma equals 5mg minus mg sine theta, and the tension terms cancel out, which gives us a equals 5g minus g sine theta over 6. So now what we have to do is we have to integrate this a couple times to figure out how fast that block is going to be going right when it reaches the top of the contraption. So first we have to remember that a equals dv dt is the derivative of velocity, which means that we can take the integral of a dt from time 0 to any arbitrary time t, and that's going to be equal to the integral of dv from v naught to any arbitrary velocity v of t. So now, since acceleration is constant, all we have to do is multiply by t to take the integral, and that's going to give us 5g minus g sine theta over 6 times t is equal to v of t, and v naught is equal to 0, so we don't have to worry about that term. Now the reason we did this, giving us a function of t for the velocity, is because we still don't actually know what t is. So this is not going to give us the launch velocity until we integrate again to figure out how fast it's going after it's moved that distance L. So in order to do that, we're going to have to use the fact that v of t is equal to dx dt, the derivative of position, which gives us the integral of v dt from 0 to big T, this is the time that the block reaches the top of the ramp, is equal to the integral of dx from 0 to L, because at that point the block has moved a distance L, and that gives us 5g minus g sine theta over 12 times t squared is equal to L. And now we can solve this, and this gives us big T, the time it takes for the block to make it up the ramp, is equal to the square root of 12L over 5g minus g sine theta. Now we can take this time and plug it into that velocity equation, and that's going to give us VL for V launch is equal to 5g minus g sine theta over 6 times the square root of 12L over 5g minus g sine theta. And if you do all the algebra and cancel out terms and whatnot, what this ends up giving us is the square root of L over 3 times 5g minus g sine theta. So that's going to be our launch velocity. Note that it has the correct dimensions, and that in a couple limiting cases, for instance, if L gets very large, the launch velocity is going to get very large. If L gets very small, the launch velocity is going to get very small. So this answer makes sense. So now what we have to do, now that we know how fast it's going to be going once it hits the top of the ramp, is we have to figure out how much higher it gets above that point. So I'm going to erase some of this to give us something to work. And now, it's been released from the tension, and now the only force acting on it is going to be the force of gravity. I'm not going to draw an isolation diagram for that, because it's only one force, but we know that that means that its acceleration is going to be g. Now, because it was launched at this angle theta, its horizontal velocity, or its vertical velocity, sorry, is going to be v sub L times sine theta. And that's all we really have to care about, because we don't care how far it's moving horizontally. We only care how high it eventually ends up going. So what this means is that we can take this launch velocity, and we can find that its average, or the average velocity as the block is flying, is just going to be the launch velocity divided by 2. And the reason we can do this is because it's accelerating at a constant rate. G is not changing at all, which means that all we have to do to find the height that it moves, delta h, is take the average velocity and multiply it by the time that it spends in the air. And that time is going to be the total vertical component, VL sine theta, divided by g, because that's the amount of time it's going to take for gravity to completely remove that vertical component, and then it'll start falling back downwards through the air. So then T is going to be, using this equation, square root of L over 3g squared times 5g minus g sine theta times sine theta. And V bar is going to be the square root of L over 12 times 5g minus g sine theta. Times sine theta again, because we're only using the vertical component. So this tells us that delta H, which is equal to H final minus H naught, is equal to the product of these two terms, which is just going to be L over 6g times 5g minus g sine theta times sine squared of theta. Now bring this h naught term over, we get h final is equal to h naught plus L over 6g times 5g minus g sine theta sine squared theta. And this is our final answer.